everybody. In this section, we're going to see a couple of examples of how systems of linear differential equations are used. One example is something called metapopulations. What's going on here is that populations are often divided up into subpopulations. With limited movement between them. So the idea here is that you've got these subpopulations that are sort of separate from each other. There may be some crossing back and forth between them, but it's limited enough that we can think of those subpopulations as being at least somewhat separate, at least somewhat different. Now the entire collection of these subpopulations is called a metapopulation. So metapopulation just means the overall population we're talking about. And we're using the word metapopulation to indicate that we're thinking of our entire population as being composed of subpopulations. Let's start with the simplest possible kind of metapopulation, namely one in which there are only two subpopulations. So let's think of them living in two areas that we're going to call A and B. Let's let x sub A of t be the number of individuals living in area A at time t. Or another way you could say that is it's the number of individuals in subpopulation A. And similarly, let's let x sub b of t be the number of individuals in subpopulation B, in other words, living in area B at time t. Now, the size of these two populations is going to change with time as individuals die, are born, and as that limited exchange between the two subpopulations occurs. In order to keep our equations and expressions, though, from being completely unwieldy, we're going to just call these two quantities x sub A and x sub B. In other words, we're not going to bother writing t every time. The t is there, even though we're just going to write x sub A and x sub B most of the time. Okay, a possible model for such a metapopulation is given by these two equations. Now, there's a lot going on in these two equations, so before we dive into what all these letters mean, let me just point out that we're looking at a system of two equations. There's one equation that gives the overall rate of change for subpopulation A, and there is a second equation that gives us the overall rate of change for subpopulation B. And I think the easiest way to figure out what these models are saying is with one of those matrix diagrams. So here we have subpopulation A with x sub A individuals in it at time t, and subpopulation B with x sub B individuals in it at time t. R of A is the per capita growth rate of subpopulation A. And R of B is the per capita growth rate of subpopulation B. By per capita growth rate, what we mean is the per capita birth rate minus the per capita death rate. Yeah, and for subpopulation A, obviously. Similarly, R sub B, the per capita growth rate of subpopulation B, is going to be the per capita birth rate minus the per capita death rate for subpopulation B. The two M's, M sub A and M sub B, are movement rates, per capita movement rates. M sub A is the per capita movement rate from subpopulation A into subpopulation B, and similarly M sub B is the per capita movement rate in the other direction. Now, when we multiply the per capita growth rate times the population size, we get the actual growth rate in number of individuals per unit of time. But births and deaths aren't the only thing changing subpopulation A. There's also movement out of subpopulation A. M sub A was per capita movement out of subpopulation A, so when you multiply that by the size of population A, you get actual loss of individuals. There's movement into subpopulation A coming from subpopulation B, and again, if we multiply that per capita movement rate times the number of individuals, but this time in population B, we get the number of individuals per unit of time going from population B into population A. That's everything that's changing subpopulation A in this model. I mean, you could imagine other things happening to change that population size, but those are the three factors we're taking into account in this particular model. So if you put those three factors together, you get the overall rate of change of subpopulation A. And then everything's exactly the same for subpopulation B, just with appropriate changes to the subscripts.